Hello, everyone. My name is Mikita Alexandrov, and I am Associate Professor at the Donetsk National Technical University. Today, I would like to present our research entitled Factors Affecting the Distribution of Extreme Values in Synchronized Three-Parity Machines. In this work, we investigate how different three-parity machines parameters influence the number of extreme weight values after a mutual synchronization. Before discussing the experiments, let me briefly introduce the idea of mutual learning. Mutual learning is a process in which two neural networks learn from each other instead of using the predefined trained dataset. In this neural cryptography, two identical neural networks receive the same random input vector and exchange only their output bits through the public communication channel. During this process, both networks gradually adjust their weights until they become identical. Once synchronization is achieved, the shared weights can be used as a common secret cryptographic key. An important advantage of this approach is that the secret key is never transmitted through the communication channel. Instead, both communicating parties independently obtain the same key after synchronization. The three-parity machine is one of the most widely used neural network models in neural cryptography. It consists of an input layer, a hidden layer, and a single output neuron. Each hidden neuron calculates the weighted sum of its inputs and produces either +1 or -1. The final output of the network is obtained by multiplying the outputs of all hidden neurons. And during synchronization, both communicating parties update their weights according to the selected learning rule. The main objective of this work was to determine which factors influence the number of extreme values, weight values after synchronization. In particular, we investigated the influence of the network architecture and the weight range parameter L. Most previous studies focused on synchronization time or resistance to attacks. In contrast, we investigate the statistical properties of synchronized weights, which have received much less attention. We investigated 7 different three-parity machine architectures, ranging from 25 to 100 synaptic weights. 3 different weight ranges were considered. It's L equals 1, equals 2, and 3. For every configuration, we performed 1,000 independent synchronization experiments. After synchronization, we counted how many weights reached the values plus or minus L. This slide summarizes all experimental results. The figure on the right shows the average percentage of extreme values after synchronization. The first important observation is that increasing the number of synapses weights does not noticeably change the proportion of extreme values. For example, when EL equals 1, the average percentage remains close to 33% for all investigated architectures. Similar behavior can also be observed for L equals 2 and L equals 3. This figure presents the main result of our work. As the weight range parameter L increases, the proportion of extreme values decreases significantly. This behavior is observed for every investigated three-parity machines architecture. The second graph also shows that the experimental results are stable, since the standard deviation remains relatively small. Therefore, we conclude that the parameter L has a much stronger influence on the distribution of extreme values than the network architecture itself. The explanation is rather intuitive. When the value of L increases, each weight can occupy a larger number of possible states. Consequently, the probability that a weight reaches one of the values becomes lower. Nevertheless, even for L equals 3, the proportion of extreme values remains significantly higher than would be expected for a perfectly uniform distribution. This indicates that the synchronization process itself tends to move some weights toward the boundaries of the allowed range. We experimentally investigated the distribution of extreme weight values after three-party machine synchronization. We found that the weight range number L is the main factor affecting the number of extreme values. Increasing L from 1 to 3 reduces the proportion of extreme values by approximately 2 times. At the same time, changing the three-party machine architecture has only a minor influence. In future work, we plan to develop a mathematical model describing this distribution. And in our opinion, these results can be useful not only for estimating the entropy of three-party machine-based keys, but also for developing new synchronization verification methods and improving exciting neural cryptographic protocols. And thank you very much for your attention.